It's ready.
Okay, so seems like we are ready to go, so welcome to my third lecture in this series. Today's topic, objects, because why not? I'm going to talk a bit about, or maybe not, because the audio system is going to drop off here. What happened? I think the battery went down.
Maybe?
Yeah.
Oh, you turned it off, maybe?
Hello? Yeah, it just went off by itself, so let's hope that this works. If not, I think I'm just going to continue to scream here. Okay, objects, because why not? Right, so I'm going to talk about how to use object-oriented programming in general, and especially in the C language, because object-oriented programming is quite useful. It's not bound to C++ only, so many people will tell you C doesn't have object-oriented programming, while C++ does. That's wrong. Technically, C++ makes it easier to write object-oriented programming, but in the end, what you can do with C is basically the same thing. You just have to be a bit more explicit in what you write. First of all, what is an object? And yeah, it went off again.
Yeah, okay.
So I might have to scream here. Let's hope that the camera captures this. And if not, then I think we might have to re-record this. I don't know. So, okay, objects. Why are they useful? Why do we need them? Basically, what an object is a computer doesn't know a lot about our real world. A computer is pretty stupid. It's just a bunch of zeros and ones interacting with each other, forming a program, and then just doing stuff. So a computer can only do what we tell it. And it can only know what we tell it. So this is the important part. A computer will only know what we tell it. And this is how I always or almost always start my lectures, because this is something that many programmers tend to forget. So it's easy to say that, well, a computer has a UI, has windows that you can open, has some other stuff. Technically, again, the rule is a computer will only know what we tell it. If we don't tell it how to do stuff, it doesn't even know how to do addition. If there was nobody telling it how to do addition, the computer wouldn't know. We have to tell it what numbers are, how numbers work. We have to tell it what strings are. We have to tell it basically everything that it does. Which has a downside, because we have to tell it everything in excruciatingly painful detail. On the other hand, we have full control over what the computer knows at any point in time. This sounds pretty abstract, so I'm going to dump this down a bit. Basically, if we have something like a number, we can tell the computer what this number is. We can say, okay, let's say we have an int, and this int is basically just 32 bits. It represents a number, but to the computer, what an int actually is it's a sequence of zeros and ones, mostly like 32 bits. But this is only the implementation or the design that we gave to an int that we chose. The computer doesn't care. To the computer, this is still a number, or not quite a number. This is just a binary pattern, a bit pattern, and if we write a function or some kind of operator so that we can tell it x plus y, we have to tell the computer how to do addition too. Mostly that's done inside of the hardware in the CPU, and which is then going to convert these numbers into another number, again another bit pattern, which then means the sum of two other numbers. So again, we tell the computer everything down to the dumbest detail basically. But of course, since we are the inventors, the people in charge of what these bits and numbers mean, we can change them. We can arrange all these different bit patterns in a way that we choose in order to represent things as simple as numbers, or maybe as complex as entire user interfaces, right? So if a computer opens up some kind of window, we also tell the computer how to do that. It doesn't know what a window is. We can only explain to it how to draw a window, how to draw the title, what to do when we press on the X button, but we're the ones telling the computer how this works. And of course, if you write a program and you compare your program with a similar program written by another person, your program and that other program are most likely going to differ. For example, you can write a function that doubles a number, so the number 2 to 4, the number 3 to 6, and so on. You can write this program in multiple ways. You can write, well, you have a number, and you do x plus x, or you do 2 times x. So what I mean is, this does the exact same thing, but there are two different ways to write it. And this doesn't only apply to these simple programs, this applies to the representation of numbers, this applies to the representation of windows, this applies to everything that's inside of the computer. So we're the ones who decide how to write an algorithm or how to implement data structures, and the computer will just run them. It's our task to make things work. And objects are one approach on how we can formulate encodings of things that we want to represent. Because again, the number 42 is something that only exists inside of our heads. For example, if you teach a kindergarten child to count, they have to learn the numbers all over again. Like, they start basically literally from 0, and you tell them how the numbers work, and the same applies to the computer. And if you teach children different ways, then they will understand numbers differently. And for example, in other countries, you count differently. For example, we say 42 in English, but in German we say 42. We say them backwards. And this actually applies to the speed at which children in school calculate. So some people reading it like 42 find it easier to write the number or to calculate with it. And if we say 42, so the digits the other way around, writing them as 24 is a common mistake that people make. So the thing that I want to explain here is representation matters. The way you deal with objects, like again 42 is some kind of object that we deal with, the way they are encoded or the way that we can work on them really shapes what we can do with them and how efficiently we can do that. And the idea is to be, or to know the tools on how to formulate and represent these objects so well that our code will run better without a lot of hassle and debugging sessions. So that's the basic idea. Okay, everything clear so far? Cool. Let's concentrate on this and not so much on the bit patterns here. As I already have told you, basically everything could be an object. For example, the number 42 could be an object. Or if you say the letter A could be an object. Or maybe even the string with the text hello could be an object. There could be different things, like a list of objects, where you have maybe some kind of list, which is itself an object, and each of its elements are also objects. These are so-called compound objects that you can like combine and build larger objects out of smaller ones. So the idea that I'm going to explain here is basically everything that you can think about and reason about and explain to other people, like a number, a digit, a letter, a string, a list. You can all explain these concepts to people, and that makes them objects. Basically everything you can explain is an object. And since we have programming languages are basically tools to help us explain objects to a computer. Even though many people will tell you that C is not an object-oriented language, the things you have, for example numbers, again, chars pointers, basically strings, or some kind of integer pointers for integer arrays, all of them are ways that C provides us with to describe these objects to the computer, which is then going to understand them as zeros and ones, just as we people understand numbers as some kind of complex representation of neurons. So that's basically the idea. And when you are a programmer, your task is to come up with objects that basically match the problem you're trying to solve. Because this is something that many people get wrong in the beginning. They often start out with their problem. Let's use a different color here. They often start out with the problem and then try to somehow break this down into the C language. So they basically say, okay, I have this problem, how can I crumble this into the C language, what the C language provides us with? So they take a problem, and then they look at C, and then they try to somehow crunch it into the C language. You might have seen that in functions that might look like, make some space, that look like this. For example, you have a string with A, B, C, and another string with D, E, F. And you want to join these two, so you say some kind of str join, and then you get back out a string called A, B, C, D, E, F, which is fine. But let's say we have the problem of joining 3 strings. What would you do? Well, str join of the first string, I'm just going to abbreviate here, I think you get the idea, and the second string, and then str join this one with the third string. But this is basically looking at what C has, which is this str join function, and then cramming the problem of joining 3 strings into what C provides us with, which is the str join function of 2 strings. But there's of course a bug inside of here, because str join mallocs a string, it allocates memory. So the return value of this call is going to allocate the string s1 plus s2 basically, which is going to be allocated and directly sent to str join with s3. Now the problem is, what happens to this result? If it was allocated, we have to free it at some point. But since we just inserted it here, it's lost. We cannot free it anymore. We have a memory leak. So what many people will do is, well, they take out this part, put this into some kind of string variable, then do the str join of the string variable and s3, and then they call free again on this s, and then they have the result. Now the problem here is this code is now taking up a lot of memory management space, although the problem itself was just appending 3 strings.